so there's an agency in Italy called the INGV, Istituto Nazionale di Geofisica e Vulcanologia, whose responsibility is to study earthquakes and volcanoes in Italy. And so there's a large scientific group there, but there's also a lot of seismic networks and geodetic networks that are there. And so you'll hear from Professor Clark and Professor Bonadonna, and they don't work for INGV, but they know everybody there, and they both have some appointments and stuff. So I don't have as much of a connection to INGV, but I know a bunch of people there too. So now let's talk about earthquakes. I'm changing this like chapter 2. Okay, so key issues for earthquakes are 3: the source, path, and site. So the source is like the snap. The path is how the how the waves get to you. They have to go through the earth, and it depends sort of how they get to you, might affect them. Also, how far they go might diminish their strength. And then the site is what's happening where you are that may influence the ground shaking. So if you're like on a soft basin, you might see amplification of waves. If you're on hard rock, it might diminish the effect. And then also the site includes like the building quality. Like if you're in an adobe, some kind of unreinforced masonry, that's not a good place to be in an earthquake. Whereas if you're in a modern wood building, usually they're pretty good. They're kind of able to go with the motion, or a really stiff steel building. So mostly I'm going to talk to you guys about source, because that's my thing. But we'll see a little bit about path and site, okay? But if you want to talk about earthquakes, just break them apart into those 3 categories. So let's talk about the kind of earthquake machine. I've sort of alluded to it, but the analogy here, this is like a one-dimensional earthquake, is a brick on sandpaper with a spring and a hand. Okay, so the hand is going to be the plate tectonic motion, the steady motion. It's just pulling. It's just like it doesn't care about anything. It's just like pull, pull, pull. But then what happens? Like, why does the brick jump? Exactly. The frictional strength is overcome. So, and the friction, what do we know about friction? There's 2 things that go with it. Well, there is that, but more like even simpler. Like just what's going on with the brick? What's important about the brick? Its mass, which is the normal force, and then the interface type. So the brick against the sandpaper means it probably have higher frictional properties than if it was like lubricated, right? And so the normal force, though, is kind of what holds it together. And then actually then the shear force is what's driving the hand pulling, or the spring transferring the pull. And so basically the shear force has to exceed the normal force times the friction. That's when it moves. And so then, but then what happens? After it moves once, what happens? It gets loaded again. So it's like, just like your fingers, right? Like I start deforming my fingers, and then at some point it flips, right? I can't predict exactly when it's going to slip, but I kind of know, right? And then sometimes it's good snap, sometimes it's bad snap. But so anyway, this is the earthquake machine. And so obviously the faster the hand moves, maybe the more frequently it jumps, all kinds of characteristics could be considered. And this is just one brick. What if you had a whole bunch of bricks that were connected also by springs? So it's like do, 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 do. So it can be more complicated, but just keep this in mind as kind of the simple 1D model of earthquakes. So yeah, so then this is just a simulation from INGV of earthquake ground motion. So this is from 2016 earthquake, and the colors are, this is like a 3D view of Italy, and the colors show the vertical velocity in a map view, sort of. And so what you can see is that's like the sound moving through the rock. So that's the path, and what we're seeing is the shaking at the site. And so we measure the effect of the earthquake like as velocity. So if you can look at this, the peak velocity, it's not very much. It's like 0.8 meters per second, 0.08, right? So it's 8 centimeters per second. So kind of moving about like this. Actually a pretty good sized earthquake. we felt that, right? And the duration might be for 30 or 40 seconds. But what's happening to the amplitude of the waves as time passes and distance increases? It goes down. The word would be attenuate. So we lose the strength with distance, right? But they go, and so you can see then if you have a seismometer, you could measure these, but you might not feel them. Like if you're in Croatia or in Sardinia or something, we might not feel it, but we would certainly be able to measure it. Like for example, this earthquake in Mexico that happened the other day, you know, it's like 240 miles, so it's almost 400 or 500 kilometers from where the earthquake was to Mexico City, but it was felt pretty well in Mexico City. It was the same kind of thing. It was more like this, and so the amplitude goes down, but the waves kind of spread out. We would say that like the frequency drops, so we don't have like the sharp motion. We have like you're like, oh, am I getting sick? No, I'm actually just feeling a far large earthquake. So so they felt it, even though it was pretty far away because it's a pretty big event. So there's lots of complications, right? It's the source, like how big was the source, but then also how far away are you, and then what was that crustal material like? Did it suck up a lot of energy, or did it let the energy pass efficiently? So any questions so far? We're almost done with our intro. Okay, so probably the last kind of background thing is about earthquake magnitude and intensity. And there's actually, I'm sorry I didn't capture this for you guys, because there was a mistake in the Washington Post yesterday on this very point. I'll explain it. So another key thing you have to remember is the distance between intensity and magnitude. So intensity is what is felt in an earthquake at a location. So it varies in space. It goes from some maximum to I didn't feel anything. The magnitude is fixed. It's just a fixed number that's the amount of energy in the earthquake. It doesn't change with space. It just, every earthquake has a different magnitude, but that's it. It's like the wattage of the lights. You know, is it a 60-watt light or is it a 100-watt light? So, what this is trying to show, and I'm not sure this is the greatest graphic, but these are different earthquakes that happened in the early, like 2010 time period, roughly, with the intensities color-coded by strength. So what this is trying to show, it mainly is like if you look at how much area is yellow. And so you can see like this magnitude 8.8 in Chile, there's a lot of yellow. In the magnitude 9, this is the 311 earthquake of Japan, there was a lot of yellow. Haiti, this one has a smaller zone of yellow, but pretty intense. This 7 in New Zealand and this El Mayor Cucupa is also decent amount of yellow. We unfortunately don't have the intensity measures for Mexico, so it's kind of cut off artificially. But if you look at these magnitude 3s, these are actually these are in this lower ones from Chicago area. There's no yellow at all. So that means it wasn't felt strongly. It was only kind of felt in a certain area lightly. This is maybe the more complicated diagram, but what we think about earthquakes then, we kind of have this wattage that we call seismic moment. And it's the amount of strain energy that's released along the whole rupture surface. And it's calculated, there's something about the rock properties, which is called the shear modulus, which it doesn't really change. And then it's kind of how much of the fault area breaks, and then what's the slippage on that surface. So you can think of like this floor, this carpet. Like if we move the whole carpet like 10 centimeters, we could take the area of the carpet times 10 centimeters times some constant, we could get an earthquake magnitude. But the equation is this m sub 0 equals mu times a times d. And the mu we know is 3 times 10 to the 10th newtons per square meter. So it's just a constant. And so here is one example we'll talk about in a little bit. This is the example of the Loquila earthquake from 2009. You can take that 10 to the 18th newton meters and convert with this equation 2/3 log 10 of that minus 6 gives us the moment magnitude, which is what we're used to, magnitude 8, magnitude 6, magnitude 7. It's a simple correction. And what this diagram then is trying to show is that this magnitude's on the left, the MW, the moment magnitude, and we're really only getting up to magnitude 9s. You know, the area is going up, so you'd have to, you start breaking the, like almost halfway through the Earth before when you get a 10, right? So you don't have enough area anywhere to get any bigger than 9s. And then this is the energy equivalent. So it's sort of showing, you know, the biggest nuclear test was a magnitude 8. Hiroshima was like a 6. Lightning bolt's like a 3.5. And then what this, I'm not always that satisfied with this diagram, but the way this the red part gets wider at the bottom is, it's what we know is the number of earthquakes per year is many more for the smaller ones. It's kind of inverse relationship between magnitude and frequency. So we have tons of little ones, and we don't have that many big ones. And so that's what that's showing, how this is real wide at the bottom, like 1 million magnitude 2s per year, but maybe only 1 magnitude 8. So when it blew up, it released a lot of energy, and because it was so energetic. So that was like based on that, like a 7.8 or something. But it's the same thing. We can compute the Newton meters of that explosion and then calculate what the magnitude would be. Yeah. So let's just look here. Oh, okay, we're almost done with this intro. So then this is the thing about intensity, which I always like. So anybody wearing their activity sensor, I don't know if anybody does that anymore, but it tells you like how much when you sleep or something, right? So there was one that I think they went broke, but it was called the Jawbone. Maybe some of you had one. And what this is showing, it was in 2014 in Napa. So this is Northern California, and this is at night. So look at the time, 9 to 1, 3 a.m. And percent of up wearers awake. So this was their sensor being kind of aggregating, like, is somebody sleeping or did they wake up? And so what you can see is that almost everyone's asleep. So in other words, only less than 20% of people are awake in that region. But then at 3:20 a.m., the earthquake occurred in the area around Napa, and you see Napa, Sonoma, Vallejo, Berkeley. So people that were near to the earthquake, most of them woke up. Whereas if you go to Modesto, Santa Cruz, which is a lot further away, the red's not that many woke up. So this is just like another way we can measure intensity in a modern sense. Like you could, if you opted in with your activity sensor, it could be a really interesting earthquake sensor, right? Okay, so then this is just the scale of how we can kind of quantify this. If you want to interview people, you want to kind of make sure they're explaining how they felt the earthquake in different ways. So, 1 through 10, where 10 is extreme, everyone's like totally freaked out, the buildings are falling down, versus 1 is you didn't even feel it. So this was actually invented by a famous Italian naturalist named Giuseppe Mercalli, who was also studied volcanoes, but he developed it to kind of have a uniform way to sort of interview people. How did they feel?